Okay, Year 13 Physics. It's time to turn this world topsy-turvy. We are going to have a look today at the reference circle and phasors. And a phasor, just to start things off right, is like a vector that's been pinned to the ground by its tail so that it can't move, but it can rotate. We are going to, by the end of this, be able to use some of our rotational motion ideas to help understand simple harmonic motion. So, to do this, consider a mass on a spring. Now if we pull that mass down, it's going to go up and down and up and down. It's going to do simple harmonic motion. It's going to have maximum speed when it's at the equilibrium position and minimum speed, 0, at each of those amplitude positions. So our mass is going to go up and down. And if we plotted what displacement looks like as a function of time, we see that the displacement goes up and down and up and down. But for solving problems this year, we're going to introduce a whole new way of thinking about this. We're going to start by drawing a reference circle. And the reference circle is a circle that's going to have a radius equal to the amplitude of motion of the motion that we're talking about. A circle, something like that. And you can see that I've continued along the dotted lines to show that the radius of that circle is just the same as the amplitude of the motion. Now the first and most important thing that we need to know about phasors is that they rotate anti-clockwise. Anti-clockwise. And so we're going to have to draw on a phasor to show the starting point of our displacement. We know it's going to start, we're going to draw it starting at the equilibrium position, and it's rotating anti-clockwise. Starting at the equilibrium position has to be somewhere on that blue dotted line, and it's going to be centered at the center of the circle. Now if we put our phasor facing that way and rotate it anti-clockwise, that's going to make the tip of the phasor, which represents the position, the displacement of our mass, that's going to make it go negative, but we want it to go positive. And so in fact we're not going to put our phasor there, we're going to point it off to the right. And so the phasor that shows the starting point of the displacement of our mass is going to be like that, and we know that its amplitude, it's the length of that phasor, is equal to the amplitude of the motion. So it's got a length A equal to the amplitude of the motion. And it's going to rotate anti-clockwise. And the beautiful thing about having a phasor that rotates anti-clockwise is that that's going to allow us to bring some constancy to our mathematics, because the displacement is constantly changing, the velocity is constantly changing, the acceleration is constantly changing. But if we model our motion with the movement of the tip of that phasor representing the vertical motion of the tip of that phasor, just thinking about its vertical motion up and down, forgetting the fact that it's going in a circle, just the up and down, if that models the motion of our mass, that phasor rotates anti-clockwise with constant angular velocity. It's going to have a constant angular velocity. Omega is 2 pi over t. Now it's really useful often to rewrite that as 2 pi f, to substitute in that the period is 1 over the frequency. And why is it 2 pi over t? 2 pi is a whole circle, 360 degrees is 2 pi, and t represents the period of motion. And so if our mass is moving up and down with a period t, then we know that phasor has to do 2 pi in t seconds. So its angular frequency, angular velocity, has to be 2 pi over t, which is 2 pi f. And it's interesting that when we're doing simple harmonic motion, we tend to call omega the angular frequency rather than the angular velocity. They're two words for the same thing. They're synonymous, but tends to be that simple harmonic motion, the omega is angular frequency, and back in rotational motion, it's angular velocity. But it means the same thing either way. So we're going to model our motion with a rotating arrow, a phasor, that's pinned down at the center, and we're going to be able to use that to find exactly what the mass has done after a certain amount of time. Let's do an example. So this is the sort of question that we are going to be faced with. We have to, for instance, know what might the displacement of the mass be if it's starting at the equilibrium position and it's moving up, and we want to know how far is it from that equilibrium position after 0.2 seconds. And so first of all, we're going to have to start by calculating its angular frequency and sketching up a reference circle. So let's have a go at those two things. You can pause the video and do it yourself if you want to, otherwise we're going to do it together. First of all, the angular frequency. I like to leave the pi in the number until the last moment because we frequently see cancellations of pi. So angular frequency, 2 pi per second. We know that pi is about 3, so the angular frequency is about 6 per second, but we're going to just leave it as 2 pi at the moment. Next, the reference circle. There's our phasor at its initial position. We know that it's at equilibrium, it's going up, and so we're going to draw our starting phasor like that. Now we want to know where that phasor is going to be after 2 seconds. So now we have to do some kind of logical thinking about where it might be so we can make our model. Now we know that it takes 1 second to go the whole way around the circle. That means that after half a second, it's going to be halfway around the circle. After a quarter of a second, it will have made it a quarter of a way around the circle, and so we're just shy of a quarter of the way around the circle. We're going to be about 4/5 of a quarter of the way around the circle, and so it's somewhere like around about there, and it has not changed length. That circle's got a constant radius because it's a circle. So we've got that angle there, and we know that we know the angular frequency is 2 pi per second, and we know that it's moving at constant angular frequency. That means that we can cheat a little bit on our mathematics, and we can just use speed equals distance over time, or angular speed equals angle over time, and we can very easily rearrange that to work out that the angle is omega t. Substitute in 2 pi times 0.2, 0.4 pi. That's that angle there, 0.4 pi. Now, our problem, we want to know what is the displacement from the equilibrium position. Let's draw on that amount. So that red line there represents the displacement from the equilibrium position. We know that when the phasor is at the top of the circle, that's when it's at the amplitude position, and so the displacement, y, is that red line there, which is pretty close to being the maximum, the 0.2 meters, but it's not quite there yet. And doing a little bit of trigonometry, we can see we're trying to find the opposite side of the triangle, and we know the hypotenuse, and we know the angle, and so we should be able to calculate this. And we can see, it's interesting, on your formula sheet they write down equations to calculate these, and you should avoid those equations at all times, but it's interesting to notice that we can write down the same equation as what's on your formula sheet. It says A sin omega t, and in fact that's exactly the same equation as what we can write down from our triangle, because omega t is just the angle and A is just the amplitude, and so looking at that we can write down, ignoring the equation, the A sin omega t, we know that the hypotenuse of the triangle is 0.2, 0.2 sin 0.4 pi. Now you need to make sure that your calculator is on radians, because that angle is measured in radians. Check that, do the calculation. Should have got 0.19, which sounds sensible, just shy of 0.2. Sensible sounding answer, we're happy with that.